Okay, now you got the main idea, so we can focus on the more technically more involved case with Fi0 being any non-negative number. In this case, I'm going to define a few things to make things a little bit easier. Let's first of all define delta I to be the maximum distance away from vertex Vi on the tree. So this is simply the farthest distance from Vi if you start moving away from the vertex on the tree. Okay? I'm going to assume each loss function Fi is defined in the domain 0 delta I with range, of course, defined by whatever the smallest value you have for the domain and the largest value you have for the domain. Okay? Now, why did I restrict it to 0 delta I? Because the points you pick on the tree network can never be any farther from Vi than delta I. Okay? That's because of the definition. These are a priori computable. All right. And the range is, of course, since this is a monotone function, the smallest you can be here is Fi0, and the largest you can be is Fi delta I. So your numbers, function values, will be in that interval. Let's do a few more definitions. Let's define alpha as, in the previous case, the maximum of Fi0 values. And let's define eta to be the minimum of the Fi delta I values. Lots of Greek letters here, huh? Okay. So P0 is, again, the problem minimize f of x, x and t, where f of x is by definition the maximum of the loss functions evaluated at the respective distances. That's the definition of that. And let's just call P1 the minimization of z subject to every loss function being less than or equal to z. Later on, I might drop the set restriction here, but just keep that in mind, okay? It's there all the time. Okay. Now, to be able to apply the inverse function to both sides, of course, z needs to be in the domain of definition of Fi inverse. Now, what's the domain of Fi inverse? It's the range here. Fi0, Fi delta I, and the range is 0 delta I. Okay? So, to be able to apply the inverse to every I want to make sure z is in the domain of definition of every Fi inverse, which means that I'm looking at the intersection of these domains. Otherwise, of course, somebody will not be well defined. Okay? So the intersection of these domains, these are simply real intervals with lower and upper bounds. So the largest of the lower bounds and the smallest of the upper bounds will determine the range where you can have your Z to have well-defined inverses. So we want to restrict Z to the maximum of the lower bounds, which means it's alpha, and the minimum of the upper bounds, which is your eta. There's a reason for defining everything. Okay. Now, of course, you want to restrict it to this range to apply the inverse, but then what happens to the original problem? You might be changing the original problem. In other words, if you append the new restriction, that restriction to this problem, and take the inverse on both sides, then that will be a new problem whose solution may or may not actually give the solution to the original. So you want to make sure that you will actually get a solution which is also a solution to the original problem. Okay? So the question is, does this restriction change optimality? Does that make you suboptimal? You cannot get any better than the optimum of, well, when you have an additional restriction, of course, you cannot get any better than the unrestricted problem. You can only get worse or stay the same. You want to stay the same. Okay. Before I argue for that, assume without loss of generality that alpha is less than or equal to eta. Now, why do I need that assumption? First of all, if that assumption does not hold, if alpha is greater than eta, then of course that interval will be non-existent, so you won't get anywhere. So you need that assumption. But one question is this assumption a well-justified assumption? So let's just make the following observation. If alpha is greater than eta, that means there's at least some index where fi of 0 is greater than some other index, f, say, j of delta j, okay? So if, say, fi of 0 is greater than, this simply says that all fi zeros are less or equal all fj delta j's. That's what it says. But if this is not the case, then you're going to have this situation. Then we have the following. If you look at f of x for an arbitrary point x on the tree, this is certainly greater or equal fi of distance x vi, because f of x is the maximum of these things. So it's surely greater or equal that, which is greater or equal fi of 0, because the argument distance is always non-negative, and the monotonicity gives you this. This is by assumption fj delta j greater than fj delta j, which is surely greater or equal fj of dx vj. Why is this true? Because delta j is the farthest you can get away from Vj. Okay? So this simply says that under such an assumption, f of x is always strictly greater than that particular fj, which means that fj has no chance of determining the maximizing loss. So you might as well just eliminate it from further consideration because it will not really change anything. Okay? So the definition of f does not need fj in that case. Sometimes, of course, the problem data might be such that you may indeed have this situation, in which case what you do is you simply, by pre-processing the data, you simply eliminate them. You don't need them. Which means, of course, if you had an m-vertex problem, your number of vertices under consideration becomes less. Okay? So if you had 20 vertices, you might end up with 15 vertices. If the smallest subtree that includes all those vertices, the surviving vertices, is the original tree, you don't have to do anything. Okay? Just do your optimization relative to that. If the surviving vertices, if you look at the set of paths connecting each pair of them, that gives you a subtree. If that subtree is a strict subset of the original tree, just delete all portions of the original tree which are not in the set, because your optimum will be in that strict subset. Did everybody follow that? Was that too fast? Okay. Okay, I guess you can relate that by simply working on examples. All I'm saying is, if your original tree is something like this, for example, and you did the pre-processing and you identified that this vertex and, for example, that vertex can be eliminated. Now, if you eliminate that vertex from the set of points that you're eligible, that will not work. That will create a hole here. Okay? You don't want to do that. But you can certainly replace this tree with the following tree, where that edge, except its one endpoint, is eliminated, because your x will never be here. Because when you put your x here, you will be getting away from all vertices, in which case, of course, you're increasing the f value. So that would be simply not, intelligent to do that. Okay? So your optimum will certainly occur at the convex hull of these surviving vertices. That's called a convex hull, if you know what the definition of a convexity means in the context of a network, which I haven't defined, so take that as a quotation. Okay? All right. At any rate, we've got this assumption. So with alpha less than or equal to n, by pre-processing if necessary, we now have an equivalent problem. Well, we do hope it's equivalent. P2, where you again want to minimize z subject to distance x vi less than or equal to z, with z restricted to the interval between alpha and eta. Sorry, that's not Z, that's Fi inverse Z. Now, the constraints here are surely equivalent to the constraints you see in the previous problem, because Fi inverse can be applied now to such Z. The problem is, how do I know that the minimizing value here, Z star, is indeed going to be in this range? Can anybody justify that? Well, if Z star is going to be in that range, of course, then I'm not doing anything wrong here. So, is the Z star obtained here? Actually, it should be a Z double star or Z cap, something else. Would that be the same as the Z star you're looking for? So, is this an equality or not? Okay, if you have Z star, which is the Z star of the original problem, is this really equal? What's the other possibility? Or greater? Okay. It can only be greater or equal. Okay, so what's the answer? So again, observation.
We showed that Z is more greater than alpha.
We already showed that, but let's just do it again. Or did I do it actually? So yeah, actually, yeah, f of x is by definition greater or equal fi dx vi for every I, which is greater or equal fi 0. This is true for every I, of course, which means fx is surely greater or equal the maximum of them, which is alpha. Okay? That's pretty much sure. This is true for every x. So f of x is always greater or equal that. How about the other one? Yes?
If the Z star value is greater than the eta value, then with a similar argument like that, we can show that this vertex will never attain this, will always smaller value, so its maximum will not be the will not determine the effect, so we can also remove
that from further consideration.
Yes, then obviously the eta value will increase because it is the minimum. Yeah, it may increase. So we can get an optimum in the range between alpha and eta.
Okay. So you're saying that this is another observation. If Z star, whatever it is, that's by definition the optimum value, happens to be greater than fj of delta j for some j, then you're saying that this particular one can be eliminated from the definition of f or the optimization. Which one are you saying? Then, of course, whatever the optimum value you have, it's going to be defined by some point, say x star, which is going to be greater or equal fj of dx vj, x star vj. That's what you're saying, I guess, right? Which is strictly, well, which is greater or equal fj of, well, actually it's not greater or equal.
Put the fj delta j before.
Over here?
First we will say yes.
Oh, I see, sorry. Okay. So this, you want to put it here. I see, okay. Okay, yeah, that's good. Yeah, and this is greater or equal fj of dx star vj, which means, of course, at the optimizing point, fj will not determine the optimum or the f value, okay? So it can be eliminated. If you do this, well, there's a slight problem with this. To be able to eliminate such things, of course, you should be able to compute them first by pre-processing, but you're not going to be able to identify such indices unless you know the actual value or the solution itself. Okay. So other than that, that's a computational barrier. But other than that, conceptually, this is actually the yeah.
If the point is first like larger than eta, then the minimizer of eta, the vertex itself, is a better solution than our solution.
Say that again. Maybe I did not follow.
If we have a solution Z which is larger than eta, then minimizer of eta, the vertex itself, is a better point than that.
Oh, I see.
So
I see. I see.
We don't have to take care. We don't have to
Okay.
deal with
Yeah.
those parts.
Okay. Okay. So if Z star happens to be greater than eta, then
The minimizer of eta, the vertex
the minimizer of
itself, is
the okay.
is a better solution.
Okay. The vertex that supplies the value of eta is a better solution. That's what you're saying. Yes. Okay. Good. Yeah. Okay. Any other comments, questions? He's saying that if Z star happens to be greater than eta, then he's saying that in that case, the vertex that supplies the value of eta is a better location than whatever you can find. But of course, in that case, we are not able to find a better solution. If Z star is greater than eta, then placing a point on top of the vertex that supplies the value of eta will not make you better. This is much clearer. I thought you had a point, but no, actually you cannot find such a point. It will not determine the value of f in that case. But here, this does the job actually. This simply says that you can eliminate such vertices from further consideration. So, let's do that. So let's reduce the vertex set to a subset which satisfy my assumption. Let me just check if this is really, okay, yeah. Well, this part is really not needed because that's automatically satisfied, okay? You can just do it this way. Okay, so with this, let's state the new problem now. Minimize Z subject to dx vi less or equal fi inverse of Z I restricted to I star, Z restricted to eta prime, because I have to recompute my eta. Also, I have to recompute my alpha, because I may have a smaller set now. So, where alpha prime is the maximum of fi0 I restricted to I star, and eta prime is the minimum of Fi delta I in I star. We simply eliminated redundant inequalities from the problem. And that's going to be my actual P2. I want to be consistent with what I wrote down here not to make a mistake. So you might want to call this P2, well, P2 prime, okay? And because of the redundancy of the constraints that are eliminated, an optimal solution to the last problem is also optimal to the original problem, as well as its equivalent version P1. Okay. So now we need to solve this. First of all, what do I know about alpha and alpha prime? Which one is larger? Yes, alpha prime is at least as large as alpha, and eta prime is greater or equal eta, right? Because I'm taking the minimum over a smaller set now. So the interval alpha prime, well, we have it. How do we have this? Okay. Alpha mı daha büyük? Yeah. It should be this way, yeah. Because we're taking the maximum over a larger set. That's what confused. Okay, so this is the situation, which means that my new interval defined by the primed parameters is a superset of the original one, which is fine. It doesn't do any, it doesn't hurt us. Okay. Is this well justified? Yes, as long as z is in between the alpha prime and eta prime value, z will be in the domain of definition of every inverse function, because we discussed that actually before. Okay. Now, what's the next step? I want to be able to now look at these constraints one pair at a time, using the necessary sufficient conditions of property 6, which simply says that for fixed z in its appropriate interval, the constraints will admit a feasible solution in X if and only if every pair of vertices has the distance between every pair of vertices is less or equal than the sum of the corresponding Fi inverse plus Fj inverse values at that z. Okay? So the constraints dxvi less or equal Fi inverse of z I in I star are consistent or admit a solution X for a given z in the interval alpha prime eta prime if and only if the distance between Vi and Vj is less or equal Fi inverse plus Fj inverse evaluated at Z. This should be true for every I and j in I star with I less than j. Should I include I equals j? Again, that will simply boil down to having 0 here on the left and Fi inverse plus Fj inverse of Z being greater or equal 0. Since Fi inverse is non-negative, Fj inverse is non-negative, so that will be automatically true. Okay. So we want to transform the last set of inequalities to the following situation. Fi inverse, Fj inverse evaluated at, let me just write Dij to not make it too long. Dij is simply distance Vi Vj. We want to have it this way with Ij in I star, I less than j, and Z between alpha prime and eta prime. I just said we want to transform, or we want to look at those inequalities in this way, because that's going to tell me that the smallest Z I'm looking for is either alpha prime or the largest left side here. Okay? Because Z has to be greater or equal each of these numbers, it has to be greater or equal the maximum of them, which means the smallest it can be is the maximum of these numbers. However, that maximum may be smaller than alpha prime, in which case, of course, Z will be equal to alpha prime. Okay? Now, that's what I want to do, but can I do it? That's the question. So, the question here is Dij in the domain of definition of this thing. So you can see how difficult these things get. I mean, they are actually quite straightforward, but you have to answer all these questions as you go along. That's how life is. So when you do research, first focus on the main idea, streamline it for a special or easy case. Once you overcome the easier case, the clean case, then insert all your other goodies that makes things difficult. Because if you decide to, if you start analyzing the more general case from the very beginning, yes, you can certainly do it, but you will go slowly, and it's going to obscure all the main ideas. You don't want it to be obscured. You don't want that curtain. Just lift up the curtain, see the actual scene, and after that, once you have a very good idea of what's going on, then you can start inserting all the things that makes the noise. That's the noise, actually. Okay. So at any rate, is Dij in the domain of this function? What's the domain of this function? I have no idea. We have to figure it. Okay? What's the domain of Fi inverse? What was it? Fi 0, Fi delta I. So Fi inverse, Fj inverse, the domain of Fi inverse plus Fj inverse is the intersection of the domain of these two, which means it's going to be the maximum of Fi0, Fj0, and the minimum of Fi delta I, Fj delta I, j. By the way, what's the range here? 0 delta I. Question?
Are they maximum are getting current range?
Well, the sum of these two functions will be defined if the argument is in the domain of definition of each function, which means that you're looking at the intersection of the domain of Fi inverse and Fj inverse. The intersection is given by the maximum of the lower bounds and the minimum of the upper bounds. Okay? So the inverse of this I better give names to these. Let me see what name I gave. Aij and Bij, I guess that's what I called them. Okay, yeah. Let's call this maximum Aij, this minimum Bij. And so here, what am I going to have? I'm going to have why? Because the range is 0 it's summation, yes. What is it? Well, when you evaluate this at the highest value, which is Bij, whatever that is, we can figure it out later, okay? But it's certainly going to be Fi plus Fj inverse evaluated at Bij. Yes, I agree. But somebody said 0, and I wrote it down. Well, why did you say 0? It may not be 0. Huh? I agree. I agree. So let's change that to that one and the other one. Bij. So my domain is now the range of this, which is, let me see if I have a name for that. Yeah, I do have a name. I call this Lij, this one Uij. So we have Lij and Uij, and the range is whatever. That thing, well, this one is actually, it's Aij, Bij. Okay, So the question is Dij in this domain, Lij, Uij? What do you say? It better be. But how do we make sure it is actually, huh? So here's the question. Is Dij in the interval Lij, Uij? Now you guys are smart, so you should be able to tell me immediately if it's greater or equal Lij, and then later you should be able to tell me if it's less or equal Uij. So first let's look at this. Is Dij at least as large as Lij? When I look at it from a nearby position, I can't really see it. What is it? Yes. Well, maybe we should actually write down the expression for these things. Let's write down Lij. How much will it be? Well, it will depend on which of Fi or Fj0 determines Aij. Okay, let's just assume Fi0 is greater than Fj0 first. So what's the Aij value in that case? Aij will be Fi0 in that case, in which case this thing will output how much? Fi inverse of Aij, which is Fi0. So we're looking at this one. How much is this? 0. Yes. So it's going to be 0 plus Fj inverse of Fi of 0. Whatever. Yeah, it's that. In the second case, well, assume they are equal. In this case, of course, it outputs 0 plus 0. In the last case, it's symmetric, so the inequality here becomes Fi inverse evaluated at Fj0 plus 0. Does that tell you anything? This is always greater or equal 0. True, because these things are always non-negative. Anything else? Does this imply Dij greater or equal Lij? Time is running. See, that could be a positive number, you see. This is also a positive number. So the middle situation, that's the easy case, but in either one, the first or the last cases, you end up with a positive number for Lij. But it may turn out that the actual distance between I and j may be less than that number. It's certainly possible. So don't be tempted to immediately conclude that distance between Vi and Vj will always be greater or equal Lij. No, it doesn't have to be. Unless there's something I'm missing here, okay? There may be something that actually forces that.
Only if they divide it with 0 and
Oh, in that case, yeah. In that case, yes. Okay? So, let me just leave you with that thought. That's my conclusion. That the distance, the actual distance between I and j can be less than Lij. Nevertheless, even if that happens, we still should be able to somehow get to where we want to go to. Okay? So I'll just leave you with that thought, and on Monday we'll figure that out. Okay? Good food for thought over the weekend.
The conclusion is true, right?
Yes. But if you can see something that actually that tells me that will not happen, I'll be very happy to see that. Okay?
I mean, we couldn't conclude that Dij is greater or equal to Lij, so
No.
when we cannot conclude this,
It's
that-
possible. Yeah, it's possible that the inequality may be reversed. Mhm.
What did they say in papers?
I don't remember. Because when I read it, I did not understand it, so I have to figure things by myself. Sometimes, you know, people just kind of say, this is so-and-so. Well, maybe they said the right thing, but at that point, I was already out of it, you know, because it just looked too complicated to me. So when things become too complicated, what I do is I just sit down and do it myself. That's the easiest, because it's much easier to do it. Yeah.